I'm Phil. I'm an engineer and manager at Capslate, as Shamoon said. But none of that matters because this is not what I work on, and it's fun and it's interesting. So the premise of this talk is that we're going to compile a subset of Lisp to assembly. We're going to use JavaScript. We're going to do it without any third-party libraries in JavaScript. We're going to do it without any third-party libraries in the compiled output, so no libc. And we're going to do it in under an hour. Sounds pretty straightforward. The point of this is to demonstrate very simple, common compiler architecture, to demonstrate that assembly, the basics of it, is not hard, to demonstrate that starting a compiler is not hard, to demonstrate that improving your compiler is not hard, and finally to demonstrate and encourage you to write your own compilers because it's a really great learning experience. So I'm already getting... I gave this talk at work a week ago, and I get so dry. So in this talk, we're going to cover parsing and code generation. And the code generation is going to be generating assembly, and we're going to also need to learn a little bit about syscalls to make this program happen. Yep. All right, so what we're going to omit is custom function definitions. That gets too complicated for an hour. We're going to omit anything that's not a function name and not a number, so no strings, no arrays. We're going to omit passing more than 3 function arguments. That's kind of arbitrary, but I just wanted to keep it simple. And we're going to ignore a whole lot of safety and a whole lot of error messages. But before we get started writing the compiler, we need to define the language that we want to be compiling. So what I'm going to say is this language is defined in S expressions, which is what Lisp uses, and that's about like where the end of our similarity to Lisp happens in this talk. So you can see these. Would love to have had a pointer, but to the right of the compiler input, you can see that there's a string that we want to be able to send to our compiler and have it generate an assembly process that runs through the operations in there to get the number 6 and produce that as the output of the program, specifically setting its exit code to be that number. So the desired use of this is to be able to call node on our script, passing it the string to be compiled, have that assembly program be printed into a file, run GCC on that file, and then run the program, and then use bash to check its exit code to make sure that the expression we compiled and evaluated was correct. Yep, all right, so let's get started. The first part of a compiler is the parser. And what the parser does is it takes a string, it breaks it out into tokens and accumulates those tokens. And ultimately, we want to produce an abstract syntax tree, which is a data structure that represents this program in the programming language that you're using. And it's much more structured. So a string has no structure. You can put anything in a string. A string does not necessarily contain a valid program, but the parser will tell us that this is a valid program and this is what its contents are. So the goal is to be able to take that input string there and produce a JavaScript array, a nested array that contains all the elements of the language broken out. So specifically, our strategy is going to be to iterate over each character of the input, recurse on left parentheses, accumulate the previous bits into a token on space and on right parentheses. So that's enough to get started on it. And I'm going to pull up my terminal, and we're going to walk through this ourselves right now. Where are you? All right, well that's, can you guys see it in the back? All right, and just to show you a little bit, let's close this out first. So here's some boilerplate, just to show you I'm not cheating or anything. So our entry point, as we said in the talk, was going to be this node script here. Inside of here, we import our parse function, we import our compile function. We grab this script, the string that you pass in as args, we parse it, and then we compile it. But right now, we're going to talk about the parser. And I'm going to cheat a little bit by having it up over here on this screen. Oh my gosh. It is getting close to my bedtime already, as my wife could tell you, so we're in it for the long haul now, though. Sorry, just pulling up my cheat sheet. All right. So we've got this concept of tokens, and tokens is important because if you think about a part of the program like the number 10, 10 consists of 2 characters, 1 and 0. So we've got to think in terms of tokens because we've got to accumulate these characters into indivisible parts like the number 10 or a variable name if it has multiple characters. So that's what we're keeping track of here. We also want to keep track of the current token as we're iterating over this input program. So the program that we're accepting here is the string, and we're going to iterate over that string. And what we're going to do is, let's switch. The default case is going to be pretty simple. The default case is where it's not a parentheses, left or right parentheses, and not a space. So in the default case, all we do is add the current character that we're iterating over to the current token. The next simple case is going to be space. So on space, what we want to do is add to the list of tokens. And I'm going to cheat here and say try to convert the current token to a number. This is, again, we're ignoring safety, we're ignoring error messages, we're just going to try to assert that it's a number, and if it's not a number, we'll store it as a string. So this is the case where we get to the number 10. Since we were accumulating the characters, 10 is not the number 10, it's the string 10, and this plus current token is going to say, if it's a string that can be converted to a number, convert it to a number, otherwise, let's just store the string. And then we need to reset the current token back so we can keep accumulating. All right, that's it for the easy cases. The hard cases are where the recursion comes in. And this always takes me hours to get right, so if and when, or just when you write your own list parser, you will take a few hours to get right and you won't be disappointed. So the preference that I have for parsing is we go recursive right here, pass in everything that we have not parsed already, all the characters that we have not yet parsed, we pass into the parse function recursively. And we're going to get back the parsed portion. Because we're hitting a left paren, we're going to get back the portion from this left paren to its matching right paren. And then there may be more of the program to deal with after that right paren. So that's what the rest is going to be. We're going to push the parsed bits to our list of tokens, reset that program string to what we haven't parsed, and reset our index to -1 so that when the loop comes back over, we started parsing after a nested S expression. And we've got some missing breaks here. All right, but so we said that parse is going to return something right here, parsed and rest, which means that we should not forget down here to return those tokens. And in this case, there's going to be nothing. This is just the end case when you've either hit the last character to be operated on and you've made a mistake, or you've hit the last right paren, yeah. So the final case that we have to deal with is, right paren. When we get to a right paren, we'll probably have come to a position like this. There's something behind us, there's some token right before the right paren, and then there's some stuff afterwards, right? So what we want to say is if there is anything, this bit right here, add it to the list of tokens. And again, we're going to do the trick here where we try to convert it to an int, or to a number. And then we need to return those tokens and the rest of the program that we have yet to parse. All right. That's a lot of stuff to deal with, but we're done. So that's the good part. We've got, what is this, 30 lines of code to parse an S expression. And you know, we've typed in stuff for a long time. Let's give it a shot. So we go into the REPL, import the parser function, parse equals require, parse. And to pretty print it, so we pass into our input function the S expression, the program that we want to parse. We're going to say, are those matching? Yeah, I think it's matching. All right, and there we've got it. So this function now parses exactly what we did. So it broke out the plus, it broke out the 2, it broke out this nested array. So we went from a string representing our program to JavaScript data structures that now represent it in all of its broken out components. And let's test it out with something more complex. All right, now we have multiple characters that was correctly broken out into the 30, and that was turned into a number, whereas the plus is not a number, so it remained a string. The cool thing about S expressions, to diverge for a second, is that not only have we parsed numeric expressions, but we've actually parsed most of the potential for a Lisp or scheme implementation. So if we want to get rid of this stuff and do assignment or function definitions, so let's say that this is the way in our language to set a equal to 2. Well, we now parse that, right? And we're just done. If we want to say this is a function that takes 2 arguments and adds them, we parse that too. So we've got like this whole language under wraps right now, and that's the reason that we pick S expressions for parsing. All right, guys, calm down. Calm down. Give me a break. All right, first, guys, come on. Basics of assembly. Got to reiterate this stuff. So assembly is an alternative representation of binary, which is one of the lowest levels that you can write programs on for your computer. It is basically a one-to-one representation of it, but people on Hacker News yelled at me saying that it was not fully one-to-one. There are special cases, so if you have questions about that, I'll tell you afterwards, begrudgingly. So in assembly, you don't have regular variables. You have a very fixed set of variables called registers. I mean, I call them variables because it's kind of easy to think about them like that, but they're called registers. They have these naming conventions, RDI, RSI, REX. These are just provided by your CPU ultimately, and you should think about them, if you don't already have a mental model for them, as global integer variables. So they're finite. There are only so many of them provided to you by your CPU, and they store integers. Additionally, so this is for just storing things in your language. Additionally, there's also a program memory, which is typically organized as a stack, an integer stack. You also have a bunch of built-in operations, really a crazy amount. If you go flipping through the Intel CPU manual, you'll see like the crazy set of instructions that you don't expect. I mean, I didn't expect it. Yeah. There's a wide variety of like floating point arithmetic and integer arithmetic and vector instructions, and it's pretty interesting. Assignment, so like variable assignment, quote unquote, you do via the move instruction. So this example here is saying move, so that means set RDI, that register RDI, to the number 1. And then finally you have function calls via the call and ret instruction, but that's pretty deceiving. So we're going to take a little bit to cover the driest part of this talk, which is the wonderful world of calling conventions. So call and ret don't mean a whole lot more than just jump to a position in code, like go to. They mean a little bit more than that, and people in Hacker News called me out on that too, so I'm not going to say that. But it's basically as free as go to. And if you know go to, it just moves you to be running in a different part of code. There's nothing in there about passing variables. There's nothing in there about returning variables. You're just moving to another part of code. So that's the level of like abstraction that assembly will give you. So what that means is that when you're either writing assembly or generating it, you've got to agree on how you call functions and how you return from them. And that's what the calling convention is about. So we're going to assume this sysv AMD64 ABI, which is what this will get you is your assembly programs will generally work on Mac, FreeBSD, Linux, not Windows. I don't really know anything about Windows, so don't ask me. And again, keep in mind that the registers are global, so anyone could overwrite. If I jump to another function, it could start overwriting the variables that I put in these registers. They're finite, so at some point someone has to overwrite a variable because you've got to store your stuff somewhere. And they're also faster than using the stack. So yeah, you could fall back on the stack, you could fall back on other program memory, but we want to keep our values in registers because it's much faster to operate on them. Right, so you've got to agree on who preserves the registers when you're calling a function and when you're returning from them. So on the caller side, what this means is these are the particular registers that a caller must save to the stack before they call the function. They must save RDI, RSI, RDX. That's because we use those registers in that order to store the parameters to the function. So RDI gets the first parameter to the function that you want to call. RSI gets the second parameter. RDX gets the third parameter. And as I said, we're omitting more than 3 parameters because it's too hard. Once you've stored them, once you've set the parameters, then you can call the function. Then after that, you need to restore the old values of those registers back from the stack in reverse order because you're now popping. And finally, when you called the function put its return value in the variable in the register REX. So these are just things you memorize and we move on from. On the callee side, it's the opposite. Make sure that you push any register's value that's not those parameter registers, onto the stack, then do your body logic, then put your return value in the REX register, and then restore the preserved registers, and then call the ret operator. All right, so we're done, and I'm going to take another drink of water before I agree to show you an example. All right, so this is a full program example of what we want to ultimately generate. So given the input program 1 plus 2 plus 9, the output should be this. So this header says we've got an entry point and just declare it as visible. This just says all program like code goes after this point, and we get into down here, the main section. This is where our logic begins. So right here, I said the first parameter to the plus operation. Let me put that here. This is us storing number 1 in the first parameter position for the outer plus call. And as I said before, we set those parameters. We needed to push these 2 values onto the stack, and then we set the parameter. And then we get into this inner function call where we push those same 2 parameters onto the stack again. Then we set the first parameter of the inner call to be 2, the second parameter of the outer call of the inner call to be 9, and then we can call the plus to do the inner plus operation. Afterwards, we've got to restore the registers back from the stack and move the result of this inner plus to the second parameter position of the outer plus, call plus, restore the registers afterward, and then finally do some syscall magic here with REX, which stores the resulting value of the entire, all the operations. All right, but we'll get more into what this last bit is here. For now, it's just voodoo magic that is there. Where'd my screen go? Where'd you go? I must have, what happened? All right, sorry. Apparently I just got rid of that because I didn't like it. All right. So now that we covered enough assembly and showed you an example of the output, we can actually get into generating that output from the result of parsing. So we are going to take the AST and produce an assembly program that computes that expression and exits with the result. And the rest of this is just a little bit of how we're going to do that, but let's just jump in. So we've got minimal boilerplate here. We've just got this helper emit function that will print things out to standard out with a certain depth. And so this prefix, we're gonna put a placeholder here for a prefix which contains that global section where we marked what was the entry point for our assembly program. Then we're going to compile the call because the entire program consists of just calls. So we're going to immediately pass the AST into this compile call function. And at the end, we're going to emit a postfix. And we'll get into the two of these later. So the compile call function needs to take two arguments primarily. The function name, because we need to put a label in the assembly to mark what the function starts, and then the args. And then finally, we're going to put in this destination bit and just treat that as magic 2. The destination argument is going to be a register to store the resulting value of this call in once it's done. So in pseudocode here, we're going to say store param registers on stack, then compile parameters, compile args, storing in param registers, then call function body, then restore param registers from stack, and maybe set the result to the destination register. All right, so how this works is we're going to iterate over the args, and we're going to say push all of the registers onto the stack. So to do that, we need to have all of the registers in a list. And this just follows that convention that I talked about, where the first arg goes into RDI, the second arg goes into RSI, and the third arg goes into RAX. RDI, yep, thank you. And we're going to iterate over them again, but this time we're going to call compile on them. Grabbing arg. So let's put some boilerplate for a compile argument function. This needs to take an AST and a destination. So maybe now you're beginning to see why this destination is useful. Down here, we said that we want to compile each arg and put it in the parameter register for that position in the parameters. So as we're iterating over the arg and calling compile on them, we're also passing in what register to store the result of that arg in there. So we put some boilerplate and compile argument. Let's do this. We call. There are only built-in functions right now, so we're going to look up the built-in function. And we need to do this because we can't put a plus In the assembly, we've got a map from plus to the word plus so that we can put that in there. And restoring the parameters from the stack is going to be the same operation like this, except in reverse. And popping. And finally, if the destination is set, we're going to say move destination. So put the result of that function call into the destination register. And just to pretty print something out here, this is just for my own sake. All right, so the only thing that we haven't done here is this compile argument function. Let's go over there. So the AST in our language can be one of only two things. It can either be an array or not an array. So we're going to say if it is an array, and what those arrays, like what those nested S expressions mean when we say array is they're another function call. So if the AST is an array, treat it as a function call. And just proxy that destination register through. And we're done there for if it's a nested S expression. And then the other case is where it's a number. And in that case, we just need to store that number into the destination register. All right, so that was a lot of typing too. And at this point, let's just see how this works. So let's see what's generated. You already saw the entry point. So the entry point takes this string here, it calls parse on it, and then calls compile with the result of what we parsed. So this should emit something. Oh, lots of undefines. All right, Phil, come on. We weren't praying to the demigods hard enough.
I think you didn't pass the depth to one of your emits.
Yeah, that's a good point. All right, that looks better. And this looks much similar. So up here, we're saving the parameter registers to the stack, setting the first argument to be 1, saving them again for the inner function call, setting the first and second arguments for the inner plus, calling plus, restoring registers, setting the results of the inner function to be the second argument, and then calling plus on the outer one and popping results finally. Okay, well that's pretty good. The only things that we haven't done in here is define that plus function. And we're going to do that in the submit prefix. So the reason that we're even having plus be a function at all, as I told you, add is a built-in operator. We're just going to do plus as a function right now just to demonstrate how function calls are made. But if this were any more efficient, it would not be making a function call for plus because there's a built-in operator and we don't need to. And we can use that. So in this prefix, we're going to say make that global marker, make the text marker, which just says this is where our program starts, and let's define plus. Nah. Okay. Oh, I'm just reading from the wrong sheets here. Yeah, this looked weird to me. All right. Add RDI, RSI. So add the first two arguments. Forgive me. Store the result in the return register, and then call return. All right, it's pretty simple. And finally, we need to mark that the main function actually begins. All right, and that's it for our prefix. So let's do this one more time. All right, so we mark main as global, we have the text section, we have the plus definition, then we have main like we had before. All right. So the last bit that we need to cover I just keep on losing my slides. Where on earth do my slides go? All right, so the last bit is what do we do with the ultimate result. So we had the outer plus, we have the inner plus, and those results need to go somewhere. What we want to do is set the exit code of the program to be the result of that computation. So to do that, our last challenging topic is syscalls. So a syscall is a special function handled by the kernel. It's the only way for regular processes to communicate outside of themselves. So you need to use a syscall every time you want to open a socket, or read from a file, or talk to another process. And in this case, we're going to be talking to another process. We're talking to our parent process by setting the exit code. These exit codes are defined by numbers, and they differ per operating system. So on Linux, the exit syscall, which sets the exit code of a process, is 60. On FreeBSD, it's 1. And on Mac, it's 0x20001. And this, the syscall operator in assembly is just like call, but we store the syscall number in the RAX register beforehand. So this is just another calling convention that we just need to know. So let's not destroy this thing. Let's bring this thing back up. And let's finish this. So the only thing we need to do in this postfix is just that final syscall to set the final value to the exit code of the program. We hardcode this because this is going to be the result of the last function call that we made. We're going to put it into RDI, which is the first parameter of the call to the syscall. We're going to set RAX to be the syscall number. How many zeros? 5 zeros. And we're going to call syscall. All right, let us give that a shot. Okay. We're going to pipe it into a prog.s file. We're getting to the end here. So this is now where we call GCC to compile our assembly ultimately into a binary that we can run. All right. Now we've got this a.out file. We run it and use bash to get the return code, and we got 6. All right, but you guys don't believe me because, you know, what do I know? So let's change this around. So 3 plus 5 is 8 plus 9. 3 plus 5 is 8 plus 1 is 9. Call GCC on it, run the program, echo the result, and it's 9. And where's my cursor? All right, so we did it. Yay. What could we have done differently? Error messages, there are no error messages here. You don't want to use this thing. This would be a pain in the butt to debug. We didn't track line numbers. We didn't track column numbers. That was just terrible. We maybe could have used a parser generator. Who knows if that would have been more useful. Comments and source in the generated code is super useful. I've got some links to projects that do this really exceptionally. We could have linked against libc to get access to the ability to create sockets really easily, to create threads, to create string utilities, create memory allocate memory. We could have targeted something that was not as insane as assembly, though, you know, what fun is that? And then we could have written tests, you know, okay. So lastly, I just wanted to provide some links in case any of this stuff was interesting to you. I will make these slides available. The calling convention, the x86-64 calling convention that we used here is kind of annoying to remember, and you'll forget it, you know, every 6 months you get back to your compiler project. Assembly programming on Mac can be particularly annoying because you've got to deal with Mac's random stack policies. So just skip that by using GCC instead of a more common assembler like NASM or FASM. The chicken scheme compilation process is pretty interesting because they generate C from scheme, and they do a really great job of commenting their output with the result of what gets compiled. So it's just very useful to read. LLVM has some great compiler tutorials. And then lastly, if you were curious why we were doing that destination-y stuff, it turns out that there's a lot of research into destination-driven code generation, which originated in a Scheme project, and the V8 team ended up using this in Chrome to generate like space-optimized code in a single pass compared to a number of more sophisticated techniques. So they were able to cut down their code by like 2/3 or something by using this destination-driven code development. And then finally, the source code of this project is on my GitHub, and there's a blog post that will also walk you through all of this as well.
Any questions? Alex? Tom, what does Tom say? No questions?